Alright, so let's say you're given this diagram of a decelerating elevator, and the question says the person on the elevator is standing on a scale, and it asks you, where's the force the scale will read while the elevator is decelerating? Would you know the answer? If not, continue watching this video. So we can start off by drawing a free body diagram, and we're interested in the forces acting on the person. So this is the reference frame that we're going to be drawing the free body diagram for. So we can identify mass equals 60 kilograms, and then we can identify the two forces acting on the mass, which is just going to be the normal force and the weight force. So these are the only two forces acting on the object. The normal force would be the force felt by the scale, because by Newton's third law, if we look at this diagram here, the person's going to be pushing down with the force, and the normal force is going to be pushing back. And this normal force is going to be equal to the person's pushing down force by Newton's third law. Apply Newton's second law equation here in the y direction, which is the summation of forces in the y is equal to mass times acceleration in the y. And we look back at our diagram, we can see that the two forces acting on the object are the normal force and the weight force, and we can define the up direction as positive, so it's going to be normal minus weight equals to mass times acceleration in the y. And we can plug in weight equals to mass times gravity. We can bring it to the other side and plug in our known values for the mass and the acceleration due to gravity. Note that the acceleration in the y is going to be the same as the elevator. Since the person is inside the elevator, they are both decelerating, so ay is going to be equal to 5.1 meters per second squared. So we can plug this all in and we get this expression here. We can compute the terms, remembering to multiply the units and the amplitudes, do a simple addition and get this for the normal force. And this is going to be the force that the scale will feel due to the person decelerating, and this value represents the apparent weight of the person, because if we look at the person's weight if they weren't accelerating, take Newton's second law equation and we plug in the acceleration equal to 0 in this case, so the normal force is just going to be equal to the mass times gravity. So if we compare these two normal force values, noting that both these values represent the person's weight, we can see that the apparent weight is going to be heavier in the case of the decelerating elevator, and this makes sense because this person appears heavier when decelerating. If you think about in real life, when you're in an elevator and it's decelerating, you feel heavier. This is due to the force of inertia, and we can see that our calculations using Newton's second and third law kind of reflected this experience in the elevator.